Okay, we're going to be starting a study in moment of inertia. And to start, let's look at the following. We have a block on a table connected by a rigid rod R. The block has mass M and the table is frictionless. We're now going to apply force to the block of mass M. What is Newton's second law as we apply that force? Well, of course, the net force, or the sum of the forces, is equal to mass times acceleration. Now let's arrange it so that F is always perpendicular to the lever arm R. Then, sum of forces is equal to mass times acceleration, and we can just simply write it as a scalar. What is the torque provided by F? Well, remember that our definition of torque is the moment arm times the force, and the moment arm times the force in this case is the magnitude of F times the magnitude of R. And so we can multiply R by the net force, which is just the force, and we multiply the mass times acceleration by R. Now, since A is accelerating in a circular motion, let's write the torque in terms of the angular acceleration. So we have that the lever arm times the force is equal to the torque. That's equal to the mass times acceleration times R. But we know that A, the acceleration, is equal to R times the angular acceleration alpha. And so we can write the torque in the form torque equal to the mass times R squared times alpha. We identify the term mass times R squared, or the mass times the distance or the length of the lever arm squared, as the moment of inertia. Now this moment of inertia plays the same role as the mass in Newton's second law in linear form. It is a resistance to angular acceleration, or to changing the angular motion.